All right, we'll start up again. So we introduced the Poisson bracket with the following definition and noted that it has an anti-symmetric property. It also follows from this definition that the Poisson bracket of the function u and a constant c has to be equal to 0. Because the partial derivatives of a constant vanish. Now, in order for you to get a sort of feeling of how you can evaluate these Poisson brackets, I'd like to give you two challenges, and then we'll discuss what kind of physical insights we can actually extract from the results. All right, so the first challenge is evaluate this Poisson bracket. And then let me write down the second one. The second one stated as follows. Let f be a completely arbitrary function of the canonical variables p and q. Find an expression for the total time derivative of f expressed in terms of f, the Hamiltonian of the system, f and the Hamiltonian of the system by using Poisson brackets. So these are the challenges. So go ahead and we'll discuss it afterwards. Okay, so let's have a look. So let's get started on one first, see where we end up. Well, the first step, I guess, should just be to insert our functions here into the definition. So we obtain and I should use a different index here, J for instance, as a summation index. something like this. Can we make any simplifications here?
The partial derivatives in the first term is the Kronecker deltas.
Mm-hmm.
INJ and KNJ.
Okay. So we have delta ij, delta kj. All right, and what about this term? Any ideas?
It's 0.
0. Why?
Because the coordinates are independent.
Yep. So keep in mind that canonical variables are always treated as independent of each other. So both of these partial derivatives are identically 0. So we can close the parentheses there. All right. Well, this should be doable. Now we only have to figure out when this sum gives a finite contribution, if it does give a finite contribution anywhere. So we have a sum for j, and this only becomes non-zero if j equals I. This only becomes non-zero if j equals k. But the product of these two combined is only non-zero if it happens at the same time, meaning that we have to have I equal k. So this is the Poisson bracket between the components of the generalized coordinates and the canonical momentum. It's the Kronecker delta. So that was the first challenge. Let's have a look at the second one. Find an expression for the total time derivative of f expressed in terms of f and h by using Poisson brackets. So how did you start?
First, expand the total derivative in terms of the partial derivatives.
Mm-hmm. So we have that f. Okay, so we have partial derivative first with respect to t. And then we know that f depends on p and q, so we should expand it. Okay, that should be a sum. And then do you mean like this?
Yes.
Okay. And then?
You use Hamilton's equations to transform the time derivatives of the coordinates into derivatives of the Hamiltonian function.
All right. So you want to replace these terms by using Hamilton's equations. And how do you know that we can use Hamilton's equations?
And because we assume the system is a Hamiltonian system.
And what do we then state about these coordinates? What's the condition on the coordinates? So if we read the problem text, I assume that f is an arbitrary function of the canonical. So that's the key word. Since q and p are canonical variables, we know that they satisfy Hamilton's equations. All right, so then we get so the first one should be q dot, which is equal to dh dpi. And then we have And the second one is P dot, which is equal to minus dH dq. Like this. This is what you had in mind? Okay. So what's the next step?
Identify the last term as the Poisson bracket of f with h.
Exactly. So we see here that precisely due to this minus term here, we have exactly this form with u and v being f and h. So it would seem then that we have accomplished our aim of expressing the total time derivative in terms of f and the Hamiltonian by using Poisson brackets. Now let's have a look at what this means. Well, it means that if there's no time dependence, if f is a conserved quantity, then this statement is equivalent to the Poisson bracket of f and h being 0. So this is actually a condition for f to be a constant of motion. So for any quantity f, we can compute the Poisson bracket with a Hamiltonian and then immediately identify whether or not it's a constant. Now, in quantum mechanics, there appears a highly similar condition. So I'll just mention that briefly. You can think of the Poisson bracket being the equivalent of what is known as commutators in quantum mechanics. Are you familiar with the term commutator? So in quantum mechanics, we have this quantity known as a commutator defined as follows. Now the key to notice here is that u and v are no longer functions, but they are operators. So this is not a scalar. It's actually a new operator. And this means that to evaluate the commutator, you have to let it act on something, act on a wave function, for instance. Now, using this commutator, you can derive something which is known as Heisenberg's operator equation. which looks like this. So I've added the hat superscript here to indicate that we're dealing with operators. So the connection here is very similar to what we consider here for Poisson brackets, namely that if the commutator between an operator and the Hamiltonian is 0, well, that means that the physical quantity corresponding to that operator is preserved or conserved, time invariant. So the sort of interpretation of these two equations is exactly the same. And we can use this to state, for instance, that, okay, say that A is the operator corresponding to angular momentum. And we're dealing with a rotational symmetric system. In that case, that has to be reflected in the Hamiltonian of the system. So you will find that the angular momentum operator and the Hamiltonian will commute. So I just wanted to mention this analogy briefly. And let me just list a couple of more formal properties of these Poisson brackets which are useful to have. Well, you have this associative property here, that you can just split it up into two separate Poisson brackets. And if you have a product in place of one of the functions, you can also split it up into two different Poisson brackets in the following way. And finally, we have this property. Now you may ask, where do all of these properties come from? Well, you can actually derive them yourself just by considering the very definition of the Poisson brackets. So just by inserting u1, u2 in the place of the first function, you will see that this holds. Or acting with a partial time derivative of the entire Poisson brackets. So these can actually be derived. Now, there is a result which can be derived from Heisenberg's operator equation, which is identical to what we obtain with Poisson brackets. And it's related to the following fact, that if you have two quantities, separate quantities, which are conserved, time invariant, then the Poisson bracket of these two quantities is a new invariant quantity. So we'll have a look at this. The result that I just stated is known as Poisson's theorem. And in order to derive it, we may use so-called Jacobi's identity. Sorry. Stating that the following three Poisson brackets, where I have now just dropped the subscript QP for convenience, should be 0. So U, V, and W are here distinct functions. So by using this Jacobi's identity, we can now understand Poisson's theorem. So let me just state Poisson's theorem first. So if f and g are constants of motion, then the Poisson bracket of f and g will also be a constant of motion. And we can see this directly from Jacobi's identity in the following way. So let W in this equation be the Hamiltonian. This brings me to the following equation. Now, by stating that f and g are constants of motion, we know that the Poisson bracket of g and h and f separately have to be 0. Yes?
But then don't you need that f and g are constants of the motion with no explicit time dependence? Because otherwise their Poisson bracket will equal minus their partial time derivative.
But if they're constants of motion, I suppose one could say that it's implicit there's no time dependence, because otherwise they wouldn't be constant.
What about
So they agree that if they're constants, there can't be no explicit time dependence. Yeah, right. So we can state that explicitly if you want, that f and g can have no explicit time dependence as well. They're constants as a function of time. And in that case, this is 0. This is 0. So it follows that this quantity here, whatever it is, also has to be a constant of motion, since its Poisson bracket with h is 0. Or if we formulated this in quantum mechanics, its commutator with h would be 0. These Poisson brackets, or alternatively, the commutators in quantum mechanics are important because oftentimes you deal with combinations of various operators and how they act, for instance in quantum mechanics, how they act on a wave function. And then it's good to know precisely how these quantities behave if you interchange them, so you get a commutator. So we can have a look at how we can calculate these Poisson brackets for combinations of various important physical quantities. So let's have a look at an example. So let's have a look at the Poisson bracket PB, just an abbreviation, formed by the classical components of the momentum and angular momentum of a particle. So consider first, for instance, just the first component, px, lx. And I'm here dropping the subscript just for brevity. Well, Lx can be expressed in terms of the coordinates and momentum, since angular momentum is defined like this. So this is the x component of the angular momentum, and by now using these mathematical properties here, we have the following. And what I've used here to obtain this equation is the Poisson bracket of two components of the momentum is 0. And you can see this just by inserting it into the definition. Now, I would also like to underline the fact that the order at which I place these quantities, for instance, placing PC after the Poisson bracket, is not of any importance here, since we're dealing with scalars. But in quantum mechanics, it will be crucial, because then operators do not necessarily commute. So here I can just throw this PC back and forth as I like, but in quantum mechanics you would have to be careful. Now, we have Poisson brackets here involving momentum and coordinates. But we have a relation for precisely this quantity, named the first challenge I gave you. Namely, it's the Kronecker delta. And since it's the Kronecker delta, we know immediately that these two Poisson brackets have to be 0, since we have different components of the momentum and the position vector. So it actually follows that Px Lx is equal to 0. Now, we have only derived this result for the xth component. However, it seems reasonable that x shouldn't play any special role compared to y or z. So it seems reasonable to expect that this should also hold for py, ly, and pz, lz. So motivated by this, consider instead the Poisson brackets between p and l, where you now have different components. So let's see if this differs from 0. So I proceed in the same way. I insert, instead of ly, a combination of the position vector and the momentum vector. So I get this. Can we simplify this somehow?
The first term will vanish.
This will vanish.
Yes.
How come?
Because x is not z, so the Kronecker delta is 0.
Exactly right. Okay. And what about the second term? Can we make the Poisson bracket go away somehow?
Well, again, you have the Kronecker delta, only this time is 1, so that turns into minus pz.
All right. So this should actually be pz.
It's the minus Kronecker delta, sorry.
Yeah. So we've then found that the Poisson bracket here is just pz. And we can obtain the result for x and y just by cyclic permutation. As follows. Now we can combine these three equations very compactly by means of the Levi-Civita tensor. So this is the expression for the Poisson bracket between any two components of momentum and angular momentum. So we'll continue with this tomorrow.